So if you do want to follow along, go to the DCC on demand and click on the oop, click on the interactive apps, CHSI Studio Workshop, and then 4 hours on account, click HIV RV 2014, and then launch. I already had one going. And so, and we're just going to kind of walk through this case study today, doing some hands-on work. So I'm going to put the sign-in sheet in the chat. So if at any point I'm not quick enough on the chat, just pop in there yourself and just kind of drop in any comments or whatnot. Just unmute yourself and speak up. That'll help with kind of getting everything together. So today we're basically going to be doing some hands-on work. So again, if you want to follow along, please do. It'll probably be more rewarding for you. But otherwise, we're just going to be kind of walking through and doing some additional stuff, both within the HVTN 505 data, then also within the RV 144 data, which I don't think we've touched yet for either of these workshops. So I'll load the necessary packages that we're going to be using. We're going to be using this package ReadXL, this table 1 package, Cable Extra, which is we're going to use to make some nicer tables, GLMnet, which is going to be used for running a lasso, Elastic Net later on, MultComp, which actually I don't think we're using, Random Forest for random forest, and then here, which is a kind of package for data sets, and then Tidyverse, which is Tidyverse. So it's a suite of packages, and I'm just too lazy to kind of load them all. So I'm going to run this. This will load up my packages. I'm going to set some paths here. So right there, this here package will say, all right, give me the location of this. So now if I do this, it gives the path to where this workshop that we're in this repo. And I'm going to give it a pass for miscellaneous and a pass for the data. And then it also gives us the sign-in code. So a little image sign-in code. If you haven't signed up already, you want to take a picture of that with your phone, a really giant picture, or, copy this into your text. All right. So the RV144 data. So RV144, I recall correctly, was a vaccine trial in Thailand. So this is from a paper published, I think, in 2020, BAMA and ICS data. I'm going to reject these cookies. Don't show this again. From 2020. So it has all these different immuno measures from these different trials that were used. So from this paper, landscapes of binding antibodies and T0 responses to pox protein HIV vaccines in Thais and South Africans, published in PLOS One. So we're going to kind of walk through the steps of, and here's kind of a link to the paper, walk through the steps to kind of take that data and to get it into a form where we can maybe use it in a couple analyses. So I'm just going to set the path here for the data, part 2 data RV144. So now we have kind of a path to where that data is living in our repo. And stop me at any point if there's any questions. So I do list files, part two data RV144. You can see like, okay, there's 6 files in there with various information. But so let's step back first and look at this HVTN 505 study. We're just going to do a simple kind of not really exciting thing, but something that's always necessary in these studies, right? Is you have to make kind of what we all call a table one, right? A demographics table showing information about the study participants. So if we open up the paper after it's cleared of, let me, any, hypothetically, we will look at the paper, but we're going to try to recreate the table one that they have in there, which shows information about the different demographics of the study participants, right? So this is something that I think we always have to do if you're publishing a paper. Um, even if maybe it's a non-human primate study, right? You may have to still publish on the ages of the animals in your model, and things along those lines. So this is something that's typically needed. So we're going to set the path. We're first going to read in this HVTN 505 data, right? So this is going to give us this huge, 20, let's see, 2,500 row data set, right? Of all the cases, all the treatment, placebo, and vaccine groups. And then read in the data dictionary. And then if we want to take a look at what the dictionary looks like, we pass it to, so this is KBL, cable, table, HVTN 505 data dictionary, cable classic. And I'll say like, okay, primary 505, what the data set name, the variable name, what the description is, and any information there, right? And so on and so on. So in R, there's always a ton of packages. This is just one package to do something, but it's something that I always, the package I like to use the most, it's called table one, where one is the number, not spelled out. And so this is a way to kind of make that contingency table it reproduce, in a kind of reproducible way. So let's go. I have the New England Journal of Medicine paper open here for the HVTN 505 trial. So let's go on down to their table one. Did I pass it? There we go. Table one. Okay. Can everybody see this? Could I get a thumbs up or thumbs down if no? All right, I got one thumbs up. Thank you, Seth. Okay. So you can see it has information on vaccine, placebo, and then there's some information over here which we're not necessarily going to look at. And then we have all this different demographic information, race, risk score, body mass, and so on. And then it gives us the N. This is like a little different from how we normally frame it, but we're going to try to get some of those same numbers. So if we, in R, it's table one, you're passing it like a formula, and you then pass the variables that you wanted to use within the data frame that you're saying. So we're saying we want it for BHV risk, BMI category. We'll also do it for numeric BMI, race full, race simplified, and then this HIV week 28 variable. And then we put a bar like for a block, and we're going to say block that by treatment. So here we can see we have BHV risk. You can see it's treating it as numeric. We have BMI category. We have BMI. We have this race information, which is full. Then we have this race here, which is treating it as numeric. Then HIV week 28. Okay. So this looks a little off, right, compared to what's in here. So we're going to recode some of these. So I'm going to take case one, and I'm going to recode the BMI variable. So remember, we have a numeric BMI value. So I'm going to say, all right, if this BMI is less than or equal to 25.34, then set it equal to less than, in quotes, less than or equal to 25.34. If BMI is greater than 25.34, set it equal to the greater than. And then I'm going to say a dot default equals NA, let's say. And then simplified race. So if we went up and we looked at this data dictionary, we can find race in here. We can see it's numeric. And we can see 1 is coded as white, non-Hispanic, and 0 is coded as non-white or Hispanic. So we can say simplified race and say, all right, if race is equal to 1, we'll measure that as non-Hispanic white. Otherwise, it'll be measured as non-white or Hispanic. And then for the HIV, we'll code this as HIV week 28 is equal to 1. They are infected with HIV, 0 non-infected with HIV. And so now we're going to pass this in and then run it. So you can see now I have BHV risk. I have this new BMI variable. I have this simplified race. I have this HIV updated treatment. And then I'm now passing this new data frame case 1 underscore lower bar mod. All right. So you can see for BMI, we have 634 that are less than 25.34, less than or equal to 25.34 in the placebo. So let's see what it was in the resulting table. So this is the vaccine. And then over here, let me find it, say 629. So we're missing something's up there, right? So we're going to have to dive into that a little bit more in a little bit. But the one thing is that the BHV risk is still being treated as numeric, while here they seem to have it in 4 categories. All right. So if we look at this BHV risk, so what I like to do is I'll just take a numeric variable and then plot it against it as a scatter plot. So let's do age instead, let's say. So you can see like, okay, this BHV risk is clearly like, it's, it has 4 levels. And so if we count it, we can do case 1 mod, and we go count BHV risk. We can say, all right, there's 919 that have a value of 0, 650 that have a value of 46, 417 that have a value of 54, and then 510 that have a value of 1, and then 8 that are missing. All right. So let's just code and say, all right, 0 is low, 0.46 low to medium, 0.54 medium to high, and 1 is high. So now we have this new BHV category variable right here, right? So it says high, low, low to medium, medium to high, and so on. Gives us the count. And so what's happening if we look at this, so if we look at the BHV risks, let's say 454 low in the vaccine group, 454 low in the vaccine group. So we're getting numbers there. So what happened is they dropped individuals, right, who are missing BHV, missing this kind of behavioral risk score, BHV for behavioral. So we're going to exclude those people then from this table 1 creation. So we're going to take this data frame, drop it. And then what I'm going to do now is take this variable, this BHV categorical variable, and I'm going to tell it to reorder it as a factor based on this variable BHV risk, which is a numerical variable. So what FCT reord does is it'll kind of reorder that variable based on some function of a continuous variable. So it'll say we wanted it to be minimum. So the default is, sorry. So basically it will look at this and say, okay, which group has the smallest median BHV risk numeric value? That's the first group. Second smallest, second, and so on and so on. So it's a way to kind of reorder a factor based on some numeric value into a way that maybe makes sense. And we're going to do something for BMI, and then I'm going to default do this for treatment. Now, what this label is doing is if we looked at the actual, these names aren't nice, right? They're kind of gross. Um, and we maybe want to give them a more self-explanatory name, and I don't want to necessarily have to change them in the text like afterwards, right? Obviously, that's an easy fix. It's just you type and you fix them in post. But let's say we didn't want to do that. So what we can do is R is just use something called a label. So we say label, and we're going to say this is our BMI. That label of that variable is body mass index. The label of the simplified race is race or ethnic group. The label of BHV cat is risk score, and then the label of HIV updated is no with an number with infection. All right. So don't worry about that warning. And so now when we do this, right, it'll say risk score. It won't say BHV cat anymore. We'll have body mass index. We'll have race or ethnic group. And then we'll have the number with infection down here at the bottom. And then you can also see that now they're ordered in a way that maybe makes sense, where it's now low, low to medium, medium to high, high. Well, before it was just default doing it alphabetically. And then if we go back to and then also, sorry, one more thing. Also on the top, come on. You see now it has vaccine first and then placebo. Well, before it was placebo first and then vaccine. Okay. And so we can see we have 1,251 in the vaccine, 1,251 in the vaccine, 454 low, 337, 208, 252, 337, 208, 252. These numbers will also match. And so we've kind of recreated their kind of table one using code. So this is a nice kind of way, if you're making a paper and you want to kind of get this information for, describing your study, that you can do this. Just something I thought kind of wanted to go over. Any questions on that? Okay. So I think next, this one actually we can do. I forgot to remove this. So actually we can kind of skip this for now, and not necessarily return to. But it was basically just looking at whether or not the we could replicate these kind of results in their paper. But hold on, I gotta go back. Am I still sharing screen? Yes. Okay, I am. All right, cool. All right. So, but we can kind of ignore that for now, because the method that they're using to do this is something that I didn't have time to reproduce. It's not your traditional just running a logistic regression to kind of get these results. So we will kind of ignore that. All right. So moving on to the RV 144. So this is going to be, now we're kind of dealing with some real messy real world data. So if you recall, there's 6 files. Can everyone see the screen all right, size-wise? Is it fine? Let's see. All right, cool. Good. All right, thank you. So we have the 6 files. Our first file is going to be this pub data, call 144. And if we look in that, there's only one sheet. So we're going to read that in using this read underscore XLX function. We give it the path, we give it the file name. And if we take a look at that, you can see it's kind of this big, 153 rows with about uh, maybe 14 columns with all these different factors where it looks like it's kind of the assay, what maybe isotype they're looking at, what function is maybe this is getting at, what gene of, say, HIV it's looking at, what clade. Then it looks like it has all this information about whether or not they match. Like there's a match between maybe, because you're looking at, say, populations in Thailand are maybe going to be very different from a population in, South Africa in terms of what viruses are circulating there. And so we see that the first column didn't have a name, so I'm just going to call that biomarker. All right. So what this is basically going to have information about all the different biomarker values that we're going to be looking at. So, a lot of information. It's kind of just meta, maybe with some nicer names, or maybe not. Some of these names are pretty rough. Um, but a lot of information in there. All right. So next up, the demographic data. Get sheets. Again, seems to only be one sheet. And then if we want to take a look at that, you can see, all right, we have publication ID. We have the study that they belong to. We have information on age, sex, treatment, what stands for per protocol. In fact, I guess whether or not they came down with HIV, race, and then we have information on BMI. You can see there's a lot of different studies in here that we're going to maybe be looking at. So here we'd have the RV144, where maybe there isn't any BMI information. Okay. So since we just did the table 1, let's kind of recreate the table 1 from the paper for this RV144 paper. So we go to this plus 1. We'll go to PubMed for now. And then we can kind of scroll down. We can get their study participants, right? So demographic information for each of these based on whether or not they received the placebo versus vaccine for RV144, HVTN97, HVTN100 in the per protocol participants. So we can get the numbers here, the age, the sex, and we can see that, like, all right, the BMI wasn't necessarily reported for some of these, right? And then they have information on race and ethnicity. Okay. So we get table 1, go age, sex, and then what I'm going to do is I'm going to put that bar for kind of block by study, and then this times is going to do it like within levels of treatment. So it'll be like study and then treatment. And then the data, and I'm going to say don't give me the overall column. So we can see the age. We can see HVTN97, and then it gives us placebo, vaccine. HVTN100, placebo, vaccine. RV144, placebo, and then vaccine. And then there's no overall column. So if I had put overall equals to true, It would have just dropped one in there. Oh. All right, there we go. If I had just left that option off, it would have just given us the overall column. All right. So if we look at these numbers and say, all right, let's look at RV 144. So we have 22 and 212. You see in the paper, sorry, 24, 212. So we see 24 and 201. So we have slightly different numbers. Does anyone know why? Okay. So the reason why is if we go back and we look, it says per protocol participants. So if you remember, there was this column, oh, data demo, per prot, right? And we didn't look at that. And you can see, all right, there's somebody here that wasn't per protocol. So if we do this again, but we basically add a filter step where we say only do this where per protocol equals 1, we'll get similar numbers. So now if we go look at our RV144, we see 24 and 201, right? Which is the numbers that were reported here. So any questions on table ones, I guess? I know we've gone over a lot, but I don't think we ever really covered this. Okay. All right. Well, we'll just continue on then. And can people hear me all right? The audio levels are fine? All right. Thanks. Okay. So next up comes the actual large biomarker data. So it's this pub data IR, immune responses, what I'm guessing the IR stands for. And we're going to read this in. So I already know that it's the first sheet and read that in. And let's look at what this looks like. View data IR. See if this breaks. All right, so we basically see, all right, we have 561 rows, and then we have 308 columns, right? So every immune response has its own column across all of these. We can see, all right, this is the CD8 response to this in CD8 producing CD154 positive response to this envelope, I'm guessing. All right. So, it's not the nicest names. And then especially in R, it's going to read in weird things like, oh, it looks like there's a line break here for this one. So, it's not going to look particularly great. So what I'm going to do is take this immune response data, and then I'm going to merge it with the demographic data. So I'm going to do left join data demo, and then I'm going to actually add here a filter step to drop to, basically only keep those that are per protocol. And then this right here is I'm going to say select the column names of data demo, then everything. So that's just making it so that the demographic variables show up first when I now look at it. So we can see, all right, it joined by pub ID. So if you ever want to be like certain that, everything's joining by the right thing, if you put in I believe it's by, you can say by pub ID. Oh, you got to put it in quotes. That'll tell it to join by pub ID because otherwise it's going to make a guess. It's going to be like, all right, what variables are the same between these two? I'll join by all of them, which sometimes is enough, right? If you know enough about the two data frames you're working with. But other times, right, you want to be a little bit more like, no, I want you to specifically join on this variable and this variable alone. So now if we look at this, I made it probably too big. So you see it has the demographic data first, followed by all of the immune response data. And you can see that this is missing for a lot of people, likely due to just differences in, what people are exposed to um, in their environments, right? Like which HIV strain is circulating. So we can take a look at this and get an idea of the count, like how many times people show up. And then something I like to do to make sure that, because in this case, every person should have one row in data demo, right? And one row in data IR. So what I'll sometimes do is I'll say like count by publication ID, right? So that gives me this. And then I'll say, hey, also count this in, like count how many this shows up. And this should say, all right, you have won 538 times. So this is kind of doing a check to say like how many times does each publication ID show up, and they all show up there only once. While as opposed to if someone showed up multiple times, you would expect this to be like one and then like two, 538. So let's say if I added a row, I added a tibble where the pub ID was equal to 097006. Now if I do this, it's going to say 537 only were counted once, and then there was one ID that was counted twice, right? Because I artificially added in this 097. This is kind of a way I like to check to make sure like joins worked and that there's the amount of data that I expect in the resulting data frames. That's just the way I like to do it though. Um, so yeah, and then here's another artificial way where you could inflate it. So where you say bind that data frame to it again, group by the pub ID, count, pull it, and table it, and it'll be like, oh, two shows up 538 times because you count two each multiple times. Okay. All right. So let's go to just the RV144 study. So we're going to take this data frame and we're going to filter to where study is equal to RV144 and where per protocol is equal to 1. All right. So now we're going to have a much smaller data frame, but we have 225, but we still have a lot of variables. So if we go and look at this manuscript, let me find one of the heat maps they make. So this is just a portion, right? They have a lot more in the paper, but there's a lot of missingness for some of these measures. So this is a heat map they made. So there's going to be a lot of stuff that we don't have. So if we look at this within this tie group, da, da, da. So you can see, right? Oh, right, obviously we don't have BMI. There's a lot of variables that we just that weren't measured in this group. So maybe we want to drop those. So there's a couple different ways we can do this. I'll show one way that's kind of maybe a little too long. And there's definitely probably faster ways to do this as well. So this is one way. Um, but so if we say take this data frame and let's say we pivot longer all the columns except for pub ID, right? So now we're going to have, oh wait, that's not going to work. And study. Study and age. It's another one. And sex and treatment. And per protocol. And infection. And race. And BMI. Okay. That should do it. So it's pivot longer, everything except for the demographics. So now we have this really giant data frame, right? 69,000 rows. And if we do that count thing I was doing earlier, right? If we do count pub ID, and then we go count in name equals NN, like each of these IDs now shows up 300, like each ID is in there 307 times, right? Because there's 307 immune response variables that we're looking at. So what you could do here is you could say group by name, because basically when we pivot this longer, let me look at this again. You can see we have this name out here now, which is like the name of the variable and the value, right? So I'm going to group by this name variable, which is the biomarker. Oops. And then I'm going to summarize. No, I'm not going to summarize. I'm going to mutate. I'm going to add all missing. And that's going to be equal to mean of is.na value. Okay. So now if we look at that, so what this is saying is that for this variable, CD4 positive, GP120, CD154, is missing for everyone in the RB144 data. This variable is only missing for about 1.8%. So we're just going to drop anywhere where all missing is equal to 1. So we're going to say all missing has to be less than 1. So now we have a lot less, 34,000. And then what we can do is I'm going to ungroup, and then I'll pivot it back wider. And again, this is how I would do it. This is probably a very inefficient way to do this. But this is just, there's so many different ways to do everything within R. This is just one of many. And there I was just making some enters so that it kind of lined up a little bit nicer. I'm going to say pivot value, values from value, and names from name. And now we're going to have this. Oh, interesting. It's still not. And then let me get rid of this all missing column. There we go. So now we're back to 225 rows. But we look at this. So we say, I'm going to call this DF, no complete missing. And we can say, all right, dimension of DF no complete missing, 225 by 162. And if we look at the original one, 316. So we've gotten rid of like 150 some columns, right? That were just completely missing for within the RV144. So that's a really long roundabout way to do this. A maybe much faster way is, so if you do just is.na on a data frame, it'll just return back basically a data frame of just trues and falses. So you can see here it's like sex, false, false, true, 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 true. So this is we can we can take a look at this. See, it's like, okay, false, true, 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 true. Then, this is kind of what R is doing in the background. It's making this giant data frame saying, all right, this is true, this is missing, this is not. So what we can do is just take the column means of that is.na. So I'll do this. And you can see it returns like, all right, this is 1, 1, 1, 1, and so on and so on. Okay, this is not missing for anyone. This is, and we can just say which of these are equal to 1. And it'll tell us, it'll say, all right, these are the ones that are completely missing. And then we can just take this and say, all right, take my data frame, drop these columns. So minus any of these where this was all missing. And if we look at that, IR, RB144, it's 225 by 161. Now, can anyone maybe gather why it's one less than this one? Take a water break. So if you recall, when I was kind of doing this on the fly, it kept giving me these warnings that these variables were categorical, right? Or they couldn't combine them. And one of them was BMI. And if you recall, BMI is also missing completely for the Thai cohort, this RV144. So I wasn't able to kind of pivot it longer, do this convoluted filtering statement, and then bring it back. So this is a way, that's the reason why we're kind of, there's a difference in how much it's moving. So in here, if we look at the column, if we kind of look at this new missing, you can see BMI is gone. We no longer have the BMI variable because it's completely missing in this group. So, any questions on that? No. Okay. Hopefully people are able to follow along. So next up, we'll just kind of remove some additional serum biomarkers. So according to the paper, they did not look at 100 serum or 500, 200 serum. So if we look at the column names of our data frame, you can see there's a few hundred serums in there. So we're going to go ahead and drop those because according to this paper, they only looked at 1 to 50 dilutions, and 1 to 40 dilutions. So we don't want the 1 to 200 or 1 to 100. So the way to do that is we can say data, and we're going to say select, and we're going to say minus any column that contains the phrase 100, this kind of string, 100 serum, or it contains the frame 200 serum. So now if we look at this data frame, you can see it's 40 serum, 50 serum, 40, 50, and so on. And then there's this kind of data up here. If you also wanted to get rid of everything, right, you could just drop anywhere that you see the word serum. So that would just be minus contains serum, and that would get rid of everything. So now if we look at this one, right? So now all of those serum columns are gone, and we're left just with these kind of, I believe, kind of cytokine response, not cytokine responses, I think, or maybe these are Bama responses, ICS responses. Okay. Um, so just, to visualize this, let's take a look at what this looks like by treatment. So this gives us an idea of, say, okay, this is what the CD4 response to envelope interferon gamma between the vaccine and the placebo. See, it removed 1 point that was outside of the range that was likely missing. And if we look at the summary of that, you can see it, get the idea of what the distribution of this is. Let me see something. Oh, cool. All right. So this geom point, right? You have to kind of add, and then you have to have this position jitter thing to kind of get it so they don't stack on top of each other. There's also a package called bswarm. So if we do library gg bswarm, and we go geom bswarm, we don't have to specify that anymore, the kind of position and the jitter and whatnot. And so now it'll kind of give it in that kind of bee swarm kind of shape if people are familiar with that. So just another way to visualize this in R. All right. Any questions so far? How about we go ahead and take a break real quick, and we'll kind of come back at 2 and kind of continue kind of walking through getting this data together. So, okay. Go ahead and start back up. So, um, we're going to, just for now, actually, let's look at this paper again real quick. All right, so they do have negative values. So let's not set values to negative. I'm gonna not do this part anymore. Because I think it was basically the data has been log 10 transformed. So we're gonna stay negative. So no positivity. Well, we're gonna allow a little bit of negative and positivity because I think some of the data is kind of a mix. So we're gonna skip this part. But basically, this is how I'll describe what this code is doing anyway. So this is taking that data frame that we had, and it's saying where it is numeric, if that value, if where the column, when I say is numeric, where the column itself is numeric, for that column, if that value x is less than 0, set it to 0. Otherwise, set it to x. Um, so, and we set it to zero in this case because maybe it thought it was some sort of normality correction, right? Where maybe they're subtracting off a naive, but and I think it's just kind of been log transformed. So we'll leave this as is. Right. So let's take this data frame. All right. And we're going to next kind of pivot it longer so that we can kind of do some summaries of it by the biomarker name. So I'm going to pivot it. And I'm going to say pivot any of the columns that are in that data RV144 demo. So if you remember this file, the biomarker column was this column with all these names, right? That are the names of the columns of which are the names of the columns in our data frame. So we're going to go through that and we're going to say, hey, if that column is in this vector here of biomarker, pivot it longer. So we do that. So now we have that much longer column, with 20,000 rows. And then I'm going to join in that information data df for demo. So I'm going to join basically all the meta information with it. So now if we look at it, say, oh, this is going to take a while to load. There we go. See, now it has all that information. Then it has the biomarker, it has the biomarker value. And then it has information on whether or not it's ICS, the factors it's looking at, the different genes, the clade, whether there's matches and whatnot. And go on down, and we can see all the different stuff. So we have serum down here from BAMA assays and so on. And one of the nice things here, so if we sort, see the negative values, so there's some negative values like negative 0.18, negative 0.16, so on. So maybe these actually haven't been log transformed. But anyway, we'll just leave them as is for now. Okay. And then what I'm going to do is I'm going to drop some of these variables that are kind of functional scores. So if we look at this data RV144 demo, and we look at factor 3, so you'd see for a lot of these, it's maybe the dilution, right? Or it's say the what they're looking at in the flow cytometer. But you also see these ones that are like score, functionality score, polyfunctionality score. So these are these measures from, I believe they're from this Compass, which is this kind of bioinformatics tool to get these kind of polyfunctionality scores of, say, immune responses. It's actually a professor at Duke, Lin who method, who sometimes teaches these courses. But for now, we're going to drop those variables from the model, from the analysis, make our life easier. So we have the resulting data frame, a little less columns. And then we are then going to say find some highly variable ones to plot. So I'm going to take this data frame. I'm going to filter to just the BAMA assatypes. I'm going to group by the biomarker and the gene. I'm going to do a summary. I'm going to use MAD, which is the median absolute distance, absolute deviation, sorry, which is like a kind of a non-parametric form of the variance, right? Your standard deviations. It's kind of to standard deviation what median is to mean, if that helps at all. On drop. So what this is going to do is it's going to give me for each biomarker and each gene, and then it's also going to give me the gene information. So I still have that. And then the kind of that variance measure, which I called var for some reason. I'm going to group by gene now. I'm going to arrange this from highest to lowest. And then within each of these genes, I'm going to grab the highest the two most varying ones. So I'm just going to slice the head of n equals 2. And then I'm going to pull that biomarker. So this is going to give me for each gene um, some highly variable biomarkers within the BAMA assay type. So the BAMA is looking at the response to these different antigens, right? And then what I can do is I can say filter, say to the non-missing, I'm going to filter to where the biomarkers in this vector of highly variable biomarkers. And then I'm going to make some box plots. So if we do that, we'll get a visualization of these 8 biomarkers, right? And then we'll have kind of, these are the ones that are most, say, the most variable in our data frame. And then if we wanted to, say, add the points, right, we could do outlier dot position equals NA, right? I think is it. Let me go back up to my what we did before. Outlier shape equals NA. And then I could add that bee swarm, let's say, on top of it. If we wanted to get information and say, have the points. So we can see for this, it's like, all right, it looks like there's a lower limit of detection thing going on here, right, for some of these variables. And then we could also reorder this. So we talked about that fact reorder function earlier. So what we could do is filter, and I can say, hey, organize these biomarkers, organize them based on this continuous value biomarker value, but the function I want you to use is this function MAD, right? Which is what we use for the median absolute deviation. And that'll then sort it for the highest varying will be at the top, then maybe some of the lowest varying will be on the kind of the bottom. This is just kind of a way to say if you want to pick out some of the more variable parameters within, like when you have like a ton of right, we have like 100 some variables that you want to look at, and you want to get an idea of what's going on, and maybe pick a few that are, say, at least have some spread in their data before you look at it. So this is something some people do within, like, say, gene expression data, which you may get to next workshop series 3 if you've signed up, right, where maybe you'll pick highly variable genes first, maybe do an analysis on. Okay. So we can also repeat this and say do it within individuals that um, just within vaccine, right? Because we saw here like some placebo, right? There's no response, right? Which maybe why would they, be if they haven't gotten they haven't gotten the vaccine. Maybe you wouldn't expect to see a placebo response, maybe unless they've already been exposed in some way and have a little bit of a memory. Um, so we could say filter to within treatment and then kind of repeat that to find the highly variable. And then we can just say pick a different variable. We'll use sex and age to see like what this looks like. So we can see kind of age and sex. Okay. Sorry, recovering from the flu. Um, so let's take this data. I'm not going to log10 transform it anymore, and let's just find variables that are associated with sex and age in the vaccinated group, right? So we're going to perform a bunch of linear regressions, looking whether or not the biomarker value is associated with age. Okay. So I'm going to filter to just for example, we're going to look at this biomarkers, right? These are all the highly variable biomarkers. We'll take the first one, this IgG3 um, response at 40 dilution to this V1, V2 epitope. Um, and we'll look at, just do a regression of it on age. So we'll take this, we got our data example, right? So we have 200, 25 people. And if we run our linear regression, gives us kind of the association with age, right? 21, 25, 25, 20, 26 and up. And so the 21 and under is the reference group, it appears. And then if we wanted to kind of actually do, analysis, we could look at, say, I'll call it run fit. I'll do summary, run fit. Boop, boop, boop. And it gives us kind of the results for each, variable. And then if you kind of wanted an overall test for whether or not age was associated with this variable, you could do ANOVA of run fit, right? Would give us kind of that overall test. I think Pishu also did it this way. If I recall correctly, it's been a while. Right, she did AOV analysis of variance, right? And so you can see, in this case, right, it gives us the same result. So when using ANOVA, you just want to be very careful of kind of the order of the parameters you're specifying. But so that's just for one variable. That's just for this V1, V2 variable, right? So let's say we wanted to do it over everything. So what we would have to do there, we could do it via a loop, which is, pretty straightforward. Or we can kind of do it via a summary statement on this long data frame. Does anyone have any question about the long data frame? Does it make sense to everybody? Okay, cool. So what we're going to do is group by the biomarker and the gene, because I kind of want the gene name. And then within each of that group, we're going to run an ANOVA. So when you run an ANOVA, let's say we say ANOVA on this LM fit, it gives back this kind of, it's actually giving back a matrix. So if we say 1, 2, it's going to give me the sum of squares, right? It's going to give me this value here, 1.13. So we can say, all right, I want 1 and I want the p-value. So that's the fifth column. So it'll give me the 0.8899. Or we could have said PR will give me that as well if you want to make sure that it gets that in case for some reason in a later version of R they decide to make this the fourth column instead of the fifth column. Now this is again just for education, not again, I don't think I've said this yet. This is kind of for educational purposes. in practice, right, when performing inference, we want to be a little bit more careful and we think about it and, we kind of write out maybe what covariates we want to look at. But here we're kind of talking about how would we do, say, this kind of immune-wide analysis over a bunch of different variables all at once in kind of a quick way. So what I'm going to do is I'm going to summarize. So let's run it on this data example first, okay? So this data example is just one biomarker. So I'm going to data example, I'm going to say group by, biomarker, and gene. And then I'm going to copy this chunk of code. The groups drop is to drop the grouping so that it doesn't like carry over and is kind of a phantom problem down the road. So if we do that, what it's going to give me is it gives me the biomarker. It gives me the gene, so V1, V2. And then it gives me the p-value for age, and it gives me the p-value for sex, right? For any association with age and any association with sex, the overall test via ANOVA. All right, so but that was just for one. So now on this longer data frame where there is, let's see how many. So I'm going to do n number of distinct biomarker. So there's 88 distinct biomarkers, right? I'm now going to do this across all of them. So if we run this, runs really quickly, right? Linear regression in general is very fast because it's just linear. There's a closed form solution. It's now going to give us this 88 by 4 data frame back, or Tibble, that has this information about each biomarker and the association with age and the association with sex. So something I'll do here, since since we're talking about presenting tables, is give this, say, as a nicer table that maybe you'd want to output to a paper or something like that. So we take this all p-values, right? And we pass this to cable. And say caption. Stop this. So we go cable, caption. So caption is the table name. So table association with age and sex. It's going to basically run that. It's going to give this kind of, doesn't look really great, but has kind of everything listed out there. So what we could do then is say, all right, cable classic, full width equals false. So then it'll give it a little bit of a nicer look, right, where it has everything, and then the resulting p-values. And if we want, we can also add a footnote, and we can say p-values are from ANOVA. And now when we run this, oh, come on. It's added a little note at the bottom, footnote, about the p-values in the resulting paper, which is kind of nice. Now, typically we wouldn't have this level of, say, scientific, like that many decimals. So what we may want to do also is we go mutate across where is numeric. And we go, let's say, I'm going to do /x. I'm going to say format C X digits equal 3. So format C will do like a kind of a scientific notation if my memory serves me correct. And you're going to see it'll kind of do a rounding there. of these to get them into kind of a three significant figures. Okay. Any questions on that? And I'm just using this cable classic, but another one people may use is cable paper. And that will give it in another different format. Um, but something that you can kind of use, and then you can just directly copy this and copy it out into a Word document. Um, there's also other packages like Flex Table, and I'm sure there's tons of other ones that can help in getting something into a manuscript ready form. Okay. All right. So let's look at this p-values again, and let's just look at one of the more, say, quote unquote significant ones, though we haven't done any multiple testing correction here, right? So we'll look at the ones that have a p-value less than 0.01. So there's two. So we're going to take our data set. We're going to filter to that vaccine group. And make sure, did we do that? We did that up here. Yeah, we did that up there. And then let's plot them again. I'm going to get rid of this position jitter thing, and I'm going to do B swarm again, because that's the new way I like to do this. I'm going to get rid of the log 10 transformation. All right. So we can get an idea what it looks like. Let me get rid of this because I'm no longer doing that. So it looks like there's no negative values here. So I'm going to add this scale y log 10 just to make it maybe a little bit clearer. But anyway, so it looks like maybe it's a little bit higher in females than in males, kind of eyeballing it, but maybe it's not super, super clear. Yeah. Any questions on this? This is a dummy example. I have no idea. This probably isn't actually biologically anything interesting. It was probably just a fluke that this happened to come out as a side. But any questions on this? Okay. All right. Well, let's look at these variables, and let's just do a QQ plot, right? Because we made a normality assumption by default by doing that ANOVA. So we're gonna take this, we're gonna filter to the vaccine group. So obviously another way what we could have done is just put this aside, right? I don't have to keep having this filter statement. I could have just made a data frame that was the filtered vaccine long, but for some reason I kept adding this in here. So get rid of the non-missing, the biomarker sex, and then we're going to make some QQ plots, right? Compared to a normal for these two variables. And they don't look great, right? Like maybe it's a little bit fine, but near the tails, it's not great. It's not the ideal kind of normal that maybe we would like to see. Um, and if we log 10 transform the data, maybe a little better. It's kind of hard to say, but it's still kind of like bleeding, a little bit in the tails, where it's kind of like falling off. So let's kind of repeat this, but do this via non-parametric. So what we're gonna do, so for sex, we'll start there, and we're gonna use a Wilcoxon rank sum test. So sex only has two levels, right? So we can use this kind of Wilcoxon rank sum test, or the Man Whitney U test. to see whether or not there's an association between, the ranks of the data. So we basically do the kind of what we've been doing. I'll add gene in here as well. Sex p-values, data long, treatment, and I'll say p-value Wilcox, biomarker value, sex. So I'm adding this at the end. So if we look at this, and I'll say data equals data example, right? It gives me back this kind of Wilcox and rank sum test. There's a continuity correction, which we probably don't need, but we'll leave in there. So, I think we covered this on day one, right? So this is a non-parametric test for whether or not two distributions are the same. Kind of, often it's called a non-parametric t-test. And what we're doing is just comparing the distribution of this biomarker value by males versus females. So it gives us this back, and then I have it's like, all right, if I do, this is like a list, and if I do p-value, it'll give me the resulting p-value from running this. So it's a way I can extract the information I want from this object. So I run this df sex p-values, and then I'm also going to do some multiple testing correction. So I'm going to do this false discovery rate multiple testing correction to account for the multiple testing I'm doing. Oh, I changed the name of it, so I'll call it. So now we have the 88 rows again. We have the Wilcoxon test, and we have the false discovery rate adjusted over here. So if we wanted to, we could say arrange by p-value Wilcox. We can see the smallest, right, and whether or not, quote unquote, it's significant. So maybe there'd be a few things that would maybe be interesting, based on kind of multiple testing correction, which we would have to have set a priori to running this. Now, if we wanted to do this via a loop, right, it would just be a matter of kind of looping through this data frame based on a vector of the biomarkers. I'm going to skip that unless people want me to do it. Would people want to see how to do this via a loop? Thumbs down or thumbs up? I don't know if there's a thumbs down option. Zoom may force positivity. Okay. All right. No thumbs. All right. So I'm going to take that as a no. Um, so if we want to do the age, instead we're going to use this thing called the Kruskal-Wallis test, which is kind of doing is a non-parametric ANOVA. Similar idea. I group by the p-value, and then I'll do the multiple testing correction. All right. So now I'm going to say p-value k dub Kruskal. And so now let's compare to what we had from the ANOVA. Okay. We'll first do sex. So we had df sex p-values, and I'm going to left join based on all p-values. So see 88 rows, we see it joined by biomarker and gene, right? So we could have also just said, okay, bi equals C biomarker gene, and it would have, given us the same thing, but it's a way to more like rigorously kind of control what you're controlling on. So we have the p-value age and the p-value sex. So we'll just plot these p-value sex. Boop, boop, boop. Yes, x equals p-value sex, y equals p-value Wilcoxon plus g on point. So I'm putting the log 10 scale just to make it easier to visualize when they're like really, really small, right? Which would mean they're quote unquote significant. And say labs, X is from ANOVA, Y is from Will Coxon. And what you see obviously is they're not, it wouldn't be one to one. But what you can see is like, okay, for the ones that are, there was some signal, you're going to see signal from both methods, right? Um, so, we could add, if we wanted to, line x-intercept 0.05. You can kind of see like if we're just thinking like, oh, is it less than 0.05? Yeah, they're basically going to be giving kind of the same final message in the inference. Which isn't that surprising given, we have like 225 people. Um, in general, as the non-parametric methods will uh, maybe have less power if the data is actually, say, normal. But in general, they're not as beholden to as many assumptions as, say, the normality is. Okay. And then we can repeat this, repeat it for age. So I'm going to say df age p-values. I'm going to say p-value Ruskell. So there was no gene in ours. And we can get, oh, what's going on here? Oh, yeah, there just wasn't anything. Sorry, it was just it was weird the shift here. So yeah, just nothing was really of interest in this one. So yeah. But so that's just kind of a comparison. They're all gonna get slightly different, but the stuff that are significant by both would probably be called significant by both. So um any questions on any of this? So these are likely being driven by maybe a couple outliers, if they weren't being picked up by the Kruskal-Wallis test. Okay. All right. So next, let's do kind of a example random forest on this RV144 data, since that was something that Pichu, I know, went over, I believe, in one of the later classes. So we're going to take this data. I'm going to group by biomarker, and I'm going to filter where there's no missing data, right? So take the data, filter to treatment, group by biomarker, filter where the sum of NAs is equal to 0. So that's going to give me a 3,400 something matrix. Um, so we're dropping a lot of biomarkers. I'm going to select just the columns I want. So publication ID, the pub ID, study, age, sex, biomarker, the biomarker value. So I'm going to drop all that meta information that we joined on about like gene, factor, vaccine match, and blah, blah, blah. Um, and then we're going to pivot it now wider to have, say, that get it back into the kind of the long form, the wide format where each biomarker has its own column. Okay. So now look at this. We have, the three variables, and we have IgG3, all these IgG3 measures. All right. And let's just pick this GP140 because it looks like a lot of these are looking at, say, like V1, V2. Actually, let's switch it up because what I did this over the weekend and it didn't work well. So we'll run this and then we'll do it a different way. So what we're gonna do is we're gonna drop out this GP41 measure from here. And we're gonna say that this now, we look at this, is going to be our kind of predictors that we're going to put into the model. And then our outcome is going to be this GP41 response. And so if we do that, so we run random forests, we have a continuous measure. I'm going to call it predicted instead of to GP41. And we can see what this looks like. And it doesn't really look like it did a great job predicting it. Maybe it, just wasn't kind of the simplest approach. Just running it base wasn't going to maybe do much. So let's repeat this, but now let's do it with one of the other, let's say pick one of the V1, V2 measures and see if it does. Because I think GP40 was kind of the only other response, and there was no other GP40 responses being measured. Right? So maybe if we pick another V1, V2 response, maybe the other V1, V2 responses will be able to kind of help correlate to kind of pick that up. So I'm going to run this again. Copy this down here. And I'm going to say, instead of this GP41, we'll pick this IgG GP70 V1, V2. Right. Make this our outcome. Get our predicted. And let's see if this does any better. Yeah, that does a lot better. It turns out if you have if you have like things within your predictors, right? Like maybe correlated measures, that maybe you'll do a little bit better in kind of these kind of predictions, comparing to say estimate this V1, V2 response based on looking at the it's likely using a lot of the other V1, V2 responses that are in the model as very, explanatory variables to kind of pick up on it and predict it. Maybe it doesn't do well where there's no response, but for the most part, pretty good. A little bit better. Okay. Now, if we wanted to repeat that with elastic net, right, penalize regression, I'm gonna set a seed and we're gonna do cross-fold validation. I'm gonna do four-fold cross-validation. I'm setting a seed because it's just because they may be, different, that the folds are reproducible. I'm gonna change this to now this V1, V2 measure. Also gonna scale it because everything's on the same scale. Get the minimum lasso. You can see what the coefficients are. You can see, oh, it looks like it's picking up on a lot of V1, V2 variables are being kind of selected as being important. And then we can say, get a prediction. We can say, with this lasso that we ran, give me the value here for this new X. Give it to me at the minimum lambda, observed. And then, we can now plot it, see how it does. Again, we kind of see a similar performance. Almost looks not identical, but pretty close between these two methods. Um, yeah, so that's kind of a down and dirty, very quick running of elastic net and lasso within these models. So if you actually looked at this, kind of give us the idea of what lambda can be looking at. The minimum mean squared error. All right. So we have some time left. So what I'm going to do next is run kind of a principal components analysis for the RV144 over everything kind of combined together. So not just an RV144, sorry. So, but like in all of the studies that are in that data frame. Is there any questions so far, though? You want to put in the chat or anywhere? Okay. All right. So we're going to go back to this data immune response demo merged. And what we're going to do, PCA example, we're going to take this. So remember, this is kind of a big 538, 316. So the first thing we're going to do is filter to just the people that were per protocol. Okay. And then I want to get an idea of what that looks like now. So we can say count, study, and then treat. Okay, so we can see we have 3 studies, and we have a mix of placebo and vaccine, all of them. Now, do people want to leave in the placebo in the PCA visualizations? Thumbs up or thumbs down? I have a Hall menthol cough suppressant. All right, I'm going to leave them in then. So what we're going to now is basically try to find some set of variables that are non-missing for everybody. Um, so let's look at this, and I'm going to, let's see. call sums is dot na across this. So let's see. Oh, nope, nope. Let me stop that. So if ever in RStudio, you just keep pressing X and it'll eventually stop doing whatever it's doing. Okay. So we want to find ones that are biomarkers, right? That are present in at least all three studies. So what I'm going to do is I'm going to say, so we may go past a little past three, if that's all right for everybody. We're going to group by biomarker. Oh, wait. So I'm going to, what's the way to do this? Okay. I'm going to do the data long thing because I'm sometimes I'm kind of brute force on these kind of ways, but um, there's definitely a faster way to do this, but I'm going to do it this way because it's kind of how my brain is wired at this point in my life. So I'm going to pivot it longer, right? Based on passing these kind of biomarkers. I'm going to group by biomarker. And study. I'm going to summarize. I'm going to say number, mean, missing. I'm going to say mean of is.na biomarker value. So what this is going to give me, and let me add a dot groups drop. So it's going to basically say like, okay, this variable is completely missing in HVT in 100. Completely missing in HVT 100. Completely missing in HVT 100. Completely missing in HVT in 97. Completely missing in HVT in 97. So what I'm going to do now is group by biomarker. And I'm going to basically, I'm going to add this check where I'm going to say summarize number complete missing. This is going to be sum of mean missing equal to 1. Okay. And so now it's going to say, all right, this is missing for 1. This is missing for, say, 0. This variable here is missing for 2 studies. This variable is missing for 2. And we're going to filter to where this value here is equal to 0. Right? Those are variables where at least it's present across all of them. So that gets us down to 65 variables. And now we have to figure out if there's any that are completely, that will maybe be a little bit, we don't have to do too much imputation, let's say. Take this data frame, and I'm going to basically do, let's say, call means of is.na, df per protocol, and I'm going to say these variables. So this pool biomarker, what that does is instead of just having a biomarker column, it just pulls it as a vector. So now I have it as a vector of all of these different variables. I mean, look at that. For the most part, they're fine. There's a few, it's like 2% missing, 2% missing, hardly any. So let's just filter to the variables that have, say, less than 5% missing. Okay. Um, so I go, which of these is less than 0.05? So we go less than 5, gives me these. I'm going to get the names. So it gives me just the names. That's still a lot, and I still think there's going to be some missing. Um, it should be fine. So let's see, because I don't want to impute right now, and I don't want to drop a ton of people, right? Because PCA requires complete data. So what I'm trying to say is like how many, I don't want to, like if it's 5% missing across 40 variables, how many people are we going to drop, right? Because it's not going to be the same 5% each time. So what I'm trying to do is I want to see how many people this is actually going to drop if we say um, do this. So I say select. We're going to look at treatment, study, and then any of less than 5. And I'm going to pub ID. We need the ID. That's always a variable that we need to keep. And I'll say age. And then I'm going to say na.omit. So this is going to drop any rows that have missing data. So we have 538 rows. Let's see what that gets us down to. The 480 people. So for now, we'll do that since this is kind of an educational we're just trying to do this, but in a real world study, you may want to then say, look to see what's going on there, and then maybe impute that data in some way to say perform principal components analysis for visualization. Okay. All right. So we have our data frame, with a bunch of different variables. We're now going to run PCA. So you go PR comp. You go DF pre-visualization. I'm going to go say select any of less than 5. I'm going to say scale equals true to make sure it scales. And that'll give us our PCA. So now we have our principal components analysis, right? And our scree plot and whatnot. But let's say we now want to visualize this by, say, study, right? You'll see those PCA plots where they show PCA1 versus PCA2, and they'll have it color-coded by different demographic variables. So to do that, we can use this package called ggfortify. And then there's this function autoplot, and we can say autoplot RPCA. So if we run that, it'll just do kind of a down and dirty. So you see PC1, PC2, right? And these are each dot corresponds to a person, right, in our analysis. And what we can do is we can say, let me see I have to remember how to do this now. So you go data equals df pre-visualization, and I can go color equals, let's say age, right? And then it'll color code it by age. Now, this is kind of within the ggplot world, so we can also then add afterwards, if we want to, theme black and white, and it'll do it in black and white. Can anyone guess probably what these two clusters are? It's treatment, right? It's placebo and vaccine, right? Which makes sense. These are pretty strong immune responses. And there's not going to be any response from the placebo group. So kind of by default, it's going to look like, they're going to appear very different from those that received a vaccine. Um, we can also then look at this by study. And you can see some kind of distinct clustering of, the different responses. So you see within these variables that we picked, right? These are kind of arbitrary variables. So you can see that the HVTN 100 is kind of separated from the RV 144 and the HVTN 97. But so this is just kind of a really simple, quick principal components analysis. We could also then say, let me see if I can remember how to do this. So if I go y equals 3, you can now see it's now plotting PCA 3 on the y-axis as opposed to PCA 2. And then if I put x equals to 2, it's now got PCA 2 down here and PCA 3. So it looks like PCA 2 is kind of picking up on the study variables, the three different studies that we have. Or it could be, then there's some other difference that if we read that paper in a little bit more detail, that would clue us into maybe why HVTN 100 is a bit different than the two others. We could also then add, you want to get an idea of the loadings. Loadings equals true. It'll add kind of the loadings, and then I think, what is it? So let's just go help autoplot.pca.printcomp, and it'll kind of give us some more information. So we say, all right, label equals true. There we go. Loadings labels. So this is about to get really busy. Yeah, that's about what I expected to happen. So you'd have to play with it a little bit more to get a true idea of maybe what's driving it. But I think y'all can think through it and think about how you would go about that. Um, so that's it for this session. If there's any questions, I can take them now. We have a kind of end of the workshop series 2 QR survey. So I'm going to post this in the chat. There's also a QR code. Oh, if people just want to scan that, that'll take you there. And then there's the sign-in sheet as well if people didn't forget to sign up. And I'll take any questions at this point. And again, your feedback's super valuable. It'll tell us whether or not we need to have a different thing for day 6, or we should keep it being kind of a case walkthrough versus maybe adding something else. Just, it really helps us in kind of workshopping and improving these. And hopefully everybody's gotten information about Workshop Series 3 and has signed up if they're interested. That'll be going over, more bioinformatics and, different assays. So it'll be mostly, not mostly, it is single cell RNA sequencing and bulk RNA sequencing. What will be covered in over that series with Josh Granick. Pishu Shu will be teaching one seminar, and then Tyler Chape will be teaching two. So, yeah, please let me know if you have any questions. I'll stay on for a bit longer, but please also fill out that survey. It is super helpful for us. So, okay. Thank you all.